Hello everybody, welcome and thank you for being here. My name is Jorge and I am the Director of the Science of Connecterra. And in this talk I would like to talk a little bit about what is it that we do and how we apply AI to what I think is a rather curious and unexpected use case. So let's get to it. When we started the company, we actually wanted to do something significant, something that had a little bit of impact in the world. And already back then we identified that there is a gap within the farming industry in how they implement technology in general. So we thought, okay, why don't we try to actually make an AI that can help us to farm and that can empower farmers of all sizes to try to be a little bit more efficient and to make the change to sustainable farming. And really try to make our farming more efficient is not something that's debatable, because as we know, by the year 2050 there will be more than 9 billion people on this planet. So that means that we will need to produce up to more than 60% more food that we produce right now, and that will be without increasing the amount of water or land that we use for it. So the industry we decided to focus on first is the dairy industry, so dairy cows, and our first product is IDA. And you can think of IDA as kind of an assistant for a dairy farmer. So the idea is that it will help you to identify the issues that you have in your farm, and is going to try to come up with solutions for what to do about them. And I think the difference that we have with respect of other products is that maybe in other products they try to show you a lot of graphs or like a lot of metrics in really big spreadsheets, and we kind of try to go away from there. So we try to provide what we call the insight. So basically it has to be very clear what is it that's going on, not necessarily showing a lot of data, but it also has to be very clear what is it that the farmer has to do to solve the situation. And actually within this concept of the insights, we can have incorporated a feedback loop where actually the farmer can go, for instance, into the app, and when he sees one of these insights he can actually say whether or not he thought that feedback was correct. And actually this is a feedback that we get, that we make labels with, and these are the labels that we actually use to train many of the models that we have. So where do you start when you want to do something like this? So let's say that you know that the subject of your study is going to be a cow, so maybe it makes sense to try to say something about their behavior. So things that the cow do are, for instance, walking, eating, ruminating, standing down, laying down. So these are the kind of behaviors that you could expect. Okay, so how do we measure that? And the first challenge that we saw back when we started the company was that there's not really a public dataset available for this kind of stuff, which partly makes sense because we were actually the first company that tried to apply machine learning to dairy cows. But it's actually the case that it was like that because there is no suitable hardware that you can actually use to come up with this dataset. So just to give you guys an example, the kind of sensors that you had available back then, they were pedometers, so it's a very simple machine that goes around the leg of the cow, and it will have like a metal ball that every time that the cow makes a step it will make kind of a click. So for every step of the cow you will get a signal with one click, and that's how you can measure how much the cow walks. But that's basically the only thing that you can measure with this thing, so in that regard it's not very useful. And the sensor that we have developed ourselves goes around the neck and is actually using an accelerometer to detect changes in movement. So this is actually the same sensor that you have in your phone, for instance. And there were all the challenges, like for example, where do you even borrow a cow? So back in the days when we didn't know the answer to this question, what we had to do was even use our office dog at the time to kind of do tests with him. So what about the implementation? I think here is kind of clear that you have to go for the deep learning approach, simply because you could try to come up with rules to kind of interpret of these different movements and patterns of movements, but I think at some point it will very soon become very complicated. And also in this case we have convolutional neural networks, which is really the perfect tool for this task. And there's also good reasons to choose CNNs over recursive networks when you go to a very low-end device, or a device that doesn't consume a lot of power. And what we started with initially was by running our models in a base station, and basically this base station is kind of a computer that sits on the farm that is responsible for collecting all of the information from all the different sensors that are running. Then it runs the model, and then it all puts the predictions to the internet and there to the cloud. And we started doing this, but then if you run this model on the sensor, then basically you can reduce the bandwidth that you use for the sensor, because then it only has to send the output, not the input, and you can use this new bandwidth that you have to actually support more cows within the same space. And we've managed to do it in such a way that the models that we train, in this case we use TensorFlow for that, we can actually run them in these devices that are really low end, and so much so that they don't even have an OS. They have to run on a really small amount of RAM. But then I think the really cool thing is that at least we managed to make the battery of these sensors to last for more than 3 years, which I think is quite an achievement also because, and to be honest, the farmers are not really going to buy a product that they have to change really much more often than that. And the reason is that even if you are very good at changing these sensors, it will still take you at the very least a few minutes per cow to change only one. So if the moment that you have any farm that has already a normal size, this will easily go into the days of work. So that's not something that many people can afford to do. So once we have this model running, and actually let's look at what is it that it produces so that we can get an idea of how this is actually used in practice. And the picture I'm showing here now is actually, I think it is 3 days in the life of a healthy cow actually. So the horizontal axis shows time, it goes from left to right, and the vertical one is also time, but in this time in percentage, so it should be interpreted as what amount of time the cow is doing a particular behavior. And these behaviors are divided in, let's say, in 2 bands. So the one on the top has to do with behaviors that have to do something with the head. So for instance, in green you have eating, in orange you have rumination. So rumination is basically taking the stuff that you have in the stomach to chew on it a bit more and then putting it back into another stomach. And the last behavior that we have here is actually idle, so doing nothing, that's on gray. And on the lower part we have behaviors that have to do with the body of the cow. So we have laying down, which is on green, we have standing up, which is on blue, and we have walking, which is in purple. So this is actually a very good example because it shows that there is kind of a daily pattern in this life. So what you would see is actually a few meals, which are in green in the top part of the graph, and these meals are usually always at the same time during the day, simply because that's the point at the time during the day where the farmer actually pushes the feed to the fences, and then that is followed by a few cycles of rumination. So the cow first eats and then it ruminates on that, and actually this rumination is usually happening when the cow is laying down, which means that the cow is actually quite comfortable. And this is another example. So this one is also a healthy cow, but this one is showing signs of estrus. And with estrus here, what we mean is the most fertile moment during the ovulation cycle of the cow. And this cycle is around 21 days long. And the idea is that you would inseminate the cow at this peak moment, and usually the window that you have for doing this is very short. But then again, if you don't get your cow pregnant, then that will happen is that you will have to wait another 21 days before you have another chance. And in the long run, these are 21 days that you will lose of milk production. So it does have a very big economical impact. And how this manifests itself in the cow is actually by making her a little bit more active and more nervous. So that's why on this graph you actually see an increase on walking times, for instance. And actually one of the machine learning models that we have within our product, it is actually detecting these kind of outliers. And already here from this image you can see that the usual trade-off that we have in machine learning between precision and recall, in this case is also a bit incomplete, because we also have to take care of timeliness because it's a time-bounded problem. So for instance, if I was to give a model with this input data, we can see that the outlier is very clear, it's very beautiful in the center of the screen. So in theory you could detect it very well, but if you look at the x-axis you will be detecting it at least 1 day or even a bit more than 1 day late, and at that point it will basically be useless to take any action on it because it will already be too late. So there is a very tricky balance between precision, recall and timeliness that you have to take care of when building a model like this. This is another example, in this case a sick cow, And here you can see very clearly how these cows seem to be ruminating more or less okay. So that would be the orange part of the graph until more or less the middle of the graph, and then it suddenly stopped ruminating for some reason. And you can still see that she seems to be eating now and then, but she's not really able to ruminate on that feed that she's ingesting. So usually when you see a rumination drop like this, that's a very big indication of something going really wrong with the cow. And what we're seeing here really is just one type of outlier, which could very well be something like a digestive issue. But depending on the kind of disease, you will get different kinds of outliers. So for example, some of them will be very short. For example, if we are talking about a fever, some diseases are very long, like lameness, and some others are even seasonal. So while it's not really a disease, but something like heat stress, it is definitely a health issue, and that happens when the cows are very warm. So they don't feel comfortable and they actually produce less milk than usual. So how will we go about training a model to detect health diseases, for instance? So here again, I think it makes sense to go for an architecture that's either an LSTM or a CNN, simply because of the time nature of the problem. And there's also some trade-offs between these two architectures. So for example, the LSTM, we see that in practice it works a little bit better. But then the good thing about the convolutional neural network is that usually the implementations that you have are faster. So what I prefer to do is to start while I'm experimenting with the CNN, and then once I have a pipeline that I can more or less trust, then I can go into the LSTM, which are a little bit slower. And something that's also interesting about the dataset that we have is that it is extremely unbalanced. So most of the cows are healthy all the time, of course, but even within the sick category, there's many different diseases and they don't all happen with the same frequency. So something very easy that you can do for that is to use something called a local loss. And this loss, what it does is actually gives more weight to the labels that happen within the less likely classes, so that your training can be a little bit more balanced. And another question is actually how long your input should be. So should I look at 6 days, 6 hours, 12 hours? What is it that I should do? And ideally you would like to use, of course, the biggest window that you can have, because that could aid in detecting some diseases that actually happen very slowly over time. But at the same time, every time that you do this, you make the problem more complicated, which means that it will also be slower to train, you will need a bigger model, and you will also need more labels to compensate for the fact that you're going to be using a bigger model. And another characteristic of the dataset that we have is that it can have gaps, which is not something that happens in every domain. And in here, what it makes sense to do is, if you only have a single model, then maybe you can alter your training to make it a little bit more robust against this kind of noise. But in the end of the day, if you're going to have, let's say, 6-7 different models that are going to have to do the same thing, it actually makes sense to have a model on its own that's basically a denoising autoencoder from which you can derive features that then the rest of the models can use, and then they don't have to take care about the fact that there can be gaps in your data. So now the question is, does this model actually work? And the good thing is that it does, and as a matter of fact, there are many issues that we can detect even days before the farmer can visually see something. And I think this is very important, because the sooner you detect a disease, it means that the cow is going to be healthier for more time. So that also means that she's going to produce more milk, so that has a very positive economic impact for a farmer. And also besides this, we actually did a test in the Wageningen University, which are very well known for doing this kind of research on agriculture. And what we tried to do was to compare actually two sets of cows. So one of them was not wearing any sensor, and one of them was wearing either sensor. So there was two different groups, and they were compared in terms of how they scored health-wise. And actually what we saw was that there was a reduction in 50% of the amount of antibiotics that the cows with IDA showed, which I think is actually really great, because especially in these days where antibiotic resistance is a serious concern. So unfortunately this is all that we have time for. I thank you everybody for listening, and I hope you found it interesting.